For problem number 4, we now have 2 exponentials in a single problem, so we need to have a different approach as to what we choose for u. All right, so it won't just be u is equal to the exponent, and here's why. When you have the exponent is just an x, we never want to do just u equals x because nothing's actually going to change, just all the x's will get replaced with u's. So there's really no difference in the function, okay? So when you see multiple exponentials, and it's something that you don't know how to simplify algebraically, what you want to do is you want to choose u is whichever expression is either longer or has a higher degree involved if you see polynomial terms, okay? So the longer expression or the one that has a higher degree involved, okay? So when I look at the numerator versus the denominator is longer, so I'm going to do u equals the denominator and see where that gets me, okay? So now the derivative of this, derivative of 1 is 0, derivative of e to the x is e to the x. So this is e to the x dx. Now this is written right here, okay? And then this piece down here, we chose to be our u. So this is what the rewrite is going to look like. I'm now going to have an integral where these two pieces are replaced by a du, and in the bottom of the fraction I have a u. This turned into a 1 over u du problem. And we should know what the antiderivative of 1 over u du is. We spent a lot of time working on that in section 5.2. The antiderivative of 1 over u is the natural log of the absolute value of u. Don't forget to write the plus c because it's a general antiderivative, okay? So that's our antiderivative. Now we just need to replace that u and we're finished. So the final answer for this is going to be the natural log of the absolute value of 1 plus e to the x, because that's what our u was, plus c, okay? So very different. It turned into a natural log problem instead of an e to the u problem. Now, I do have a follow-up question, and this is to tie back in some of the stuff that we did back in chapter 4. My follow-up is, how would this change if we had the integral, same integrand, e to the x, 1 plus e to the x dx, but now I put bounds on the integral sign. How would it be different if I put bounds on the integral sign? All right, we know that if we have bounds, that eventually we're going to get a numerical answer out of this. But the integration process stays exactly the same. We just don't need the plus c anymore, okay? So we've already done the u, the du, the rewrite, and the integral. So we know that this integral is equal to the natural log of the absolute value of 1 plus e to the x. But now we're going to evaluate it with the bounds from 0 to 1. We can drop the plus c, and we can plug in the bounds, okay? So this is going to give us a kind of weird-looking answer. But you could potentially see situations like this, especially if you take calculus again in the future, okay? So we are going to plug in the b value, the top bound first, the upper bound first. Natural log absolute value of 1 plus e to the first. Subtract the lower bound plugged in. Natural log absolute value of 1 plus e to the 0, okay? Now, e is a special number, it's on your calculator, so e to the first power, we can find that on a calculator. We've got the natural log of the absolute value of 1 plus e minus the natural log absolute value of 1 plus e to the 0. Any number to the 0 power is 1, so this is really 1 plus 1, this is 2. And if I type that into a calculator, I'll get my final answer, all right? If you wanted to, you could condense this. Because there's subtraction between two logarithms, you can make that the natural log of a division problem, and you could do 1 plus e over 2. But realistically, you'd be getting a decimal answer for this one way or another. So this is approximately 0.62 if you plug it in on a calculator, okay? Now, we're not going to do a lot with the bounds involved, but I wanted to remind you of how that fundamental theorem of calculus plays out when we do have bounds on an antiderivative on an integral problem. Okay, so that's it for problem number 4.